Hi, so today we are going to learn force between two parallel current carrying conductors. Two parallelly placed current carrying conductors carrying some current experiences force. If the current is flowing through the same direction, then there is attractive force. Here in this very case, you can see that current is flowing along the same direction in the two wires, wire A and wire B. The current are IA and IB. Now we are interested to find magnetic force acting on any one wire. And we know that when any wire is kept in any magnetic field, it experiences some force. Current wire is placed in a magnetic field. Then the wire experiences a force. Now here you can see that the two current carrying conductors are kept near to each other. And we also know that a current carrying conductor produces magnetic field. So A wire is producing magnetic field in the vicinity of B wire, and B wire in turn produces a magnetic field in the vicinity of A wire. So let there is a magnetic field BA in the vicinity of B produced due to A. So we will be using two concepts and we can find the force acting on these wires. So the first concept is Biot-Savart's law. Two things we will be using. First one, Biot-Savart's law, and second thing we will be using Lorentz force. When any current carrying conductor is kept in any magnetic field, then it experiences some force which is called Lorentz force. So firstly we will be obtaining magnetic field at point P on wire B due to wire A and due to current IA. So magnetic field from 1 at wire B at point P due to wire A due to current IA in wire A. So this magnetic field is produced by IA, so it is your BA. Now BA, using Biot-Savart's law, it is equal to mu naught upon 4 pi 2I, and I is your IA, 2I upon R, and the distance I have taken between the point and the current carrying conductor is D. So here your distance is D. This is the magnetic field, and direction can be obtained using right hand thumb rule. And you will find that the direction of B is going inside the plane. It is going inside the plane when the wire B is on the plane. Okay, so here you can see the direction of BA is along inside the plane, and length element I have taken on wire B in the direction of current IB. It is along upward direction, you can see. So therefore now we use Lorentz force. That says that force on any wire. Here we are interested in force on wire B due to wire A. It is force on wire B due to wire A. Okay. Now the Lorentz force. This is here. Let me delete. That must be equal to I dl cross B. B at wire B, and this B is equal to BA. So we will be writing here BA. Therefore, the force on wire B due to wire A is equal to I, and the cross product of it, dl, magnitude of dl, magnitude of BA into sine of angle between the two. And you can see that angle between dl vector I have taken on the wire, and B is 90 degree. Here this angle is your 90 degree. And if you find cross product of DL and B, putting a screw at this very place, and when you turn the screw from first vector to second vector, you will find that it is going inside. It is moving clockwise, and thus it is moving inside. And so you can see that the product of the two vectors, that is force vector, has direction found by screw rule is towards wire A. Okay, so these two things we noted. Now here angle is sine 90 degree, and sine 90 degree is 1. So FBA is equal to I, and DL, we should take length DL, into BA. BA we have written already, mu naught upon 4 pi 2IA upon D. And sine 90 means 1. Therefore, force on B due to A per unit length, if you divide with length, you will obtain that it is equal to mu naught upon 4 pi 2, and this I. Okay, one more thing. Here current flowing in wire B is IB. Current flowing in wire B should be taken as IB. IB. Wire B, IB. Okay. So mu naught upon 4 pi to Ia Ib upon D. This is your force acting on wire B. Which is along wire A. Now similarly, if you proceed, you will find that force on wire A due to B per unit length comes equal to the same value, same magnitude, mu naught upon 4 pi to Ia Ib upon D. This is the force acting on wire A. Due to wire B and is directed towards wire B. So here we observed that force on wire A due to wire B is equal to force on wire B due to wire A, and only the direction is opposite. So here we comes at Newton's third law, starting from Biot-Savart's law and Lorentz law. We reach at Newton's third law, and this can be attained only when the current is steady one. This is possible only when the current is steady and not alternating current. So we observe that when current is flowing in the same direction, then force is attractive. So similarly, you will find that when the current is flowing in opposite direction, force will be repulsive. So when currents are flowing in the same direction, force is attractive. And when the currents are flowing in opposite directions, the force is repulsive. So we found that unlike the Coulomb's force, in which the two similar charges repel each other and two dissimilar charges attract each other, here the case is different. The two similar current means two currents in the same direction are attractive and two currents in opposite directions are repulsive. Now using this formula, we can also define 1 Newton value, 1 ampere. So definition of 1 ampere. Firstly, let me write the formula. Force per unit length is equal to, I am writing magnitude of it. It is equal to mu naught upon 4 pi 2 I1 I2 upon the distance r. Okay. So if you take r is equal to 1 meter, I1 is equal to I2 is equal to 1 ampere, then force per unit length F upon L comes equal to mu naught upon 4 pi 2, 1 into 1 by 1. And so therefore this force per unit length comes equal to 2 into, this has value 10 to power minus 7. So this much Newton per meter. From here we can define 1 ampere. So when two parallel current carrying conductor placed at a distance of 1 meter are experiencing a force of per unit length (2 into 10 to power minus 7 Newton per meter), then the current flowing in the wire is the current in the wires is 1 ampere each. So this is how you define 1 ampere. This is 1 ampere is defined. And this definition is totally theoretical one, because practically you cannot achieve this value, as along with this magnetic field due to current carrying conductor, there is magnetic field due to earth. Until you replace this, just get rid of this magnetic field due to earth, you cannot reach to this value. So it is theoretical value only of 1 ampere. Practically it cannot be obtained until the wires are of infinite length and the magnetic field of earth is just removed from there.